Let's consider beam design at this point. In a design of a beam, there's a couple of things you usually know. You know how long it needs to be, you know how much load there will be and where, and you know where supports will be located for the beam. All these things are necessary before you can really begin a good beam design. And what you're trying to find is what material you want to use for the beam and the particular size and cross-sectional shape of the beam. There's a lot of factors that affect the beam design itself. One of them, and the most important, is safety. The purpose of a beam is to support a transverse load. And so if the beam can't do that safely, you've got a problem. Often beams are used for structural applications or support of machinery, and these things can be very heavy, and failure is simply not acceptable of a beam. The cost is another important consideration. If you cannot afford to make the beam, you can't support the load. You can't buy it. So cost is another very important and significant concern in beam design. So inexpensive materials are often preferred in order to make the beam, but you need materials that are inexpensive yet strong. The appearance of the beam can sometimes be important. If the beam is exposed, the aesthetics of the beam might be important. The appearance of the beam in the sense that it needs to look strong enough to be trustworthy. The appearance can be important. The size of the beam is probably a more important factor, where if the beam can't fit in a certain cross-section, or you need it to go around some obstacle, then that might affect the size and the cross-section shape. The weight of the beam can be significant. A lot of times we neglect the weight of beams because they are so strong. However, the reality is that beams do have some weight, and if the supports can only support so much weight, well, adding beam weight to it causes an additional load on the supports. But also the weight of the beam itself has to be supported by the beam. So that's another very important consideration. The beam needs to be a thing that can be worked in with the rest of the structure. You have to be able to attach it rigidly to the rest of the structure. And of course the particular desired shape has to be available. So the availability of various types of materials or shapes, and there are standards around these things, but the availability of these things is another concern. Here's some guidelines for design stresses in beams. Now this table is in Chapter 7, but it's also at the back of your book. I've asked you to mark this page several times. If you haven't yet, please do. You're looking for design guidelines. There's a whole page, and I think it's 721. I think I have that one memorized, but I'm not certain. So look it up and make sure you have the page mark that has all the design guidelines listed in it. It's a really handy page to keep available. So these design guidelines, if you notice, are based on the type of loading, whether it's static, repeated, or a shock impact type loading, and whether the beam is made of a ductile or a brittle material. So the ductile material for a static load, you notice we compare against the yield stress, and the idea is that you don't want the ductile beam to fail, and yielding is considered a failure often. But a repeated load, in other words a fatigue load, we compare against the ultimate strength SU. Why is that? Well, fatigue strength is not the same as ultimate strength. Okay, let's get that straight. But it correlates well with fatigue strength. So fatigue and ultimate strength sort of go hand in hand, and the big thing that differentiates the two and that makes a difference in getting the fatigue strength from the ultimate strength, a big determining factor there is the surface finish of the material, because fatiguing is a type of failure where cracks basically propagate throughout the material, and the smoother the surface is, the fewer the cracks are available to propagate, and so the less that'll happen. So the surface finish does make a difference, and we'll study about fatigue a little later in more depth. But for a rule of thumb, a quick estimate, the maximum design stress for a repeated, or in other words a fatigue load, should be about 1/8 of the ultimate strength or so. For impact or shock loading, which can give very large loads rapidly, the recommendation here is the ultimate strength by 12. For brittle materials, of course, they don't yield, and so none of the design stress guidelines here involve yield strengths. They're all ultimate strengths. And of course, brittle materials can fatigue as well. So repeated loads, you see the factors larger, and shock loads higher still. Now, what we're doing here is designing the beam based on the maximum stress in the beam. So in our equation where we're calculating the maximum stress, MCO over I, for example, we're trying to design against the stress that exists in the outer fibers of the beam. Now we're also assuming with these equations, or with these design guidelines, that the material of the beam is homogeneous and it's isotropic, and all that means is that it's the same material throughout, and that material behaves the same regardless of what direction it's loaded in. So its material properties do not depend on directional loading. Things like composites are, well, not all, but some composites their strength depends on the direction of the load. So that's what we're saying here, is we need the material to not depend on the direction of loading. Now on the other hand, if the beam's material has a different strength in compression versus tension, then you have to consider both. You have to consider both the compressive stress and the tensile stress in the beam and make sure that the beam is safe against both tension and compression. Very often beams are designed based on codes. And so for buildings and beams we have a simple design guideline here, but the fact is structural engineering is a whole branch of civil engineering. You're not going to get out of this course and go design I-beams for the next skyscraper. There's a lot more to it than that, and there's a lot more to the codes than what we have in our text. But often beam design is done based on codes, and the idea here is that using first principles is well and good, but the codes are based on first principles with a lot of experience and a lot of other practical factors added into the beam design so that the beam ends up being safe. So codes are actually very valuable. They're not a pain in the sense that they help your design. They make your design better. And so if you're in an industry where beams are designed using codes, you should certainly use those codes and learn the codes as well. There's a lot more to beams than what we have time to present here in just one class. But here are some guidelines for beams made of steel from the American Institute for Steel Construction, I think that's AISC if I remember right, and the Aluminum Association. So beams can be made of either, and you notice that there's some guidelines here for both steel and aluminum beams. Now in the aluminum codes you'll notice that there's two different calculations for the design stress, one based on the ultimate strength and the other one based on the yield strength, and what's recommended here is just to use whichever one gives you the lower value. Each aluminum has a different yield and ultimate strength, and so it's often that one will give you a lower design stress versus yield and the other one will give you a lower design stress versus the ultimate strength of the beam. So that's the Aluminum Association recommendation for beams in buildings or building-like structures that you don't expect a lot of variation in the loads. Just like the polar section modulus, there's a section modulus in our beams as well. And the thing is, if you think about the bending stress, and knowing that the bending stress is what usually causes a beam to fail, it's MC over I. But C is a geometric property and I is a geometric property of the beam as well. So you'll notice that the section modulus is often listed in the back of your book. You should go to the back of the book now and look for the beam tables. There are tables that show very common cross sections of aluminum beams or aluminum extrusions, I should say, and steel beams. And these are pages that are well worth marking now. I will of course refer to them as I go through example problems, but please notice that the section modulus for each beam is given, and it's a very convenient thing to have because instead of having to always calculate MC over I, you just calculate M over S. And that will give you the maximum stress because notice that the section modulus S is at the outer fiber, right? It's I over C, where C is the distance from the neutral axis to the outer fiber. So this is a very convenient thing. Rather than having to calculate or use C and I all the time, you can simply use the section modulus for standard shaped beams or standard cross sections. Now there's some stress concentration factors also in our appendices. One is in A21, and here we're talking about a groove in a shaft, and you might look at this and say, well, wait a second, I thought we were talking about beams. Well, it turns out that shafts actually behave much like beams. They are rotating beams, and so they are essentially repeated load type beams. If you have a machine element at any point along the length of the shaft, like a gear or a pulley or a bearing even, those things will apply radial loads to the shaft. And so you can think of a shaft as simply being a beam where there are radial loads at various points along the length of the beam. Now, of course, you could draw shear and moment diagrams for these beams as well, and then the features along the length of the beam might end up generating stress concentrations, like, key seats or groove rings or shoulders, things like that. Now, you might think back to the restrictions we had on MC over I and say, well, wait a second, I thought you said that the beam needs to be uniform along the entire cross section, or along the entire length. The cross section has to be the same. What I really meant by that is that the beam needs to not change a lot in the local area. So if you look at the smaller diameter section of the shaft, there's a big change at the shoulder, but to take care of that change we use a stress concentration factor, or there's material cut out the key seat, so there we would use a stress concentration factor, and so on, even with the ring groove. So there are several different stress concentration factors in the back of your book for taking care of the sudden changes in geometry along the length of the shaft. Another important concept with beams is something called the flexural center. So you see a C channel here, and the C channel is first of all shown unloaded, and then a load is placed at the center of the upper flange. And what you'll notice is that the beam will not simply flex out at the end and deflect, rather it will also twist. And that can be problematic, because if a beam begins to twist, and of course this would be a cantilevered beam, but if the beam begins to twist, well then you've got trouble, because that's almost like a buckling phenomenon where the strength of the beam is significantly reduced. Now, of course, this doesn't have to be even a cantilevered beam. This could be a beam that's attached on the other end. If you apply a load at the center and it's not at the flexural center, then the beam can still twist along its length, and this is of course problematic. So how do you locate the flexural center? Well, there are ways to do it, but with math, but it's much easier to just look it up on a table. So there is a figure or a table in your book, and you need to mark it. It's in chapter 7. It looks just like this, and it shows you the location of the flexural center, called Q, as a function of what type of geometry you've got, what size it is, and so forth. If you have a symmetric cross section, then the shear center is always at the center of that beam. So an I-beam, for example, we don't need a table like this, because it's symmetrical about a vertical axis, and in that case the shear center is just at the centroid. But for these asymmetric sections, the shear center is not at the centroid. So we have to load the beam at the shear center, otherwise the beam is going to twist. So, for example, if you have C channel and it's oriented vertically, as you see on the left, the flexural center actually turns out to be off to the side. Q is to the left of the beam, and so you have to add a bit of material there so that the load can be applied at the flexural center of the beam in order to avoid twisting. Now, obviously, if you take that C channel and you turn it 90 degrees, now it's symmetric about a vertical axis, and you just load it in the center. Now its flexural center Q is at the centroid of the shape. Now, some beam shapes are more efficient than others. In other words, some beam shapes make better use of the material that the beam is made from. Remember, we talked about twisting a shaft, and that a hollow shaft is better than a solid shaft because you're putting material in the area where the stress is the highest and eliminating material in the areas where the stress is the lowest. Well, beams are the same way. And so we'll start off with item A, which is a simple beam. You might use a 2x4 or a 2x6 or something like that for a beam. And this beam could be made more efficiently. In fact, you could cut out a bunch of material from this beam and not change its strength or its deflection characteristics much at all. And so going from A to B, you notice a lot of material has been carved out from the sides of the beam and looks more like what you'd know as an I-beam. An I or an S or a W shape is what it's known as in industry. And the shape in B is much lighter than the shape in A, uses a lot less material, and yet is almost as strong. And the reason that beams can be made like this is because due to the transverse nature of the load, the moment is generated primarily from the maximum stresses that occur at the outer fibers. So the upper and lower flanges carry the bulk of the stress that generates the moment in the beam. The other material in the center is not doing much. Just like in the drive shaft, the middle of the drive shaft material just doesn't do much, so why have it there in the first place? Item C is actually much like item B, where the web has been broken into two parts. I actually, long story, I remodeled my house quite a lot, and I've used several beams along the way. Some of the beams that were originally in the home, there was a room in the center of the home that was open to the outdoors. I guess they realized after about a year when they built it in the 70s that that was a bad idea, because there are tall trees next to my house, and I'm sure they had tons of leaves that just fell into the center of the home that they'd have to put in, trash bags or something and cart them through the house to get them out. I'm sure that became a pain very quickly. So apparently they put a almost flat roof section over it. I've since removed that and changed the roof line so that it drains water much better. But when I got up there, when I first bought the house, and I got up on this almost flat section, well, it must have been about 14 foot wide and about 30 foot long. They had run 2x6s the length of that ceiling, so you could get up there, and a 2x6 is only 5.5 inches tall, 1.5 wide. And I've forgotten how many they had up there. I think they may have put them on 2-foot centers, even at 16-inch centers. You could get up there and jump on it, and it was like a trampoline. I mean, it literally moved and deflected and bounced that much. So of course I ripped those out, and for a while it looked like a dinosaur had come along and taken a bite out of the middle of my house. But I restructured the roof and changed it to a much more classic design. It looks a little more aesthetically appealing, and it drains water much better, and it's much stronger than what was up there. But another place I used beams in my home, as part of that remodeling job, there was a center section in the house that was the original sort of entryway. I took that out, and it ended up that there was actually a basement beneath it. There was this small concrete room, maybe, what was it? Probably 10 feet by 14 feet, I think. So it was 10 feet deep and then 14 feet wide. And I wanted to put a porch there instead of the area that had been above it. So there were concrete walls. Just imagine a 10 foot by 14 foot floor plan, concrete, 8-inch concrete walls. Well, I ran some metal beams across the 10-foot dimension of that, and then I ended up forming it and pouring concrete on top, so that I basically have a front porch there. Well, the beams that I used, I could have bought I-beams, but I actually chose square tubing, and the reason I chose square tubing, I could have chosen rectangular, but the square was just as cheap, and I ended up choosing the thickest wall I could get because I didn't want them to be very tall. For water drainage purposes, I had to cut the walls of that room down a little bit, I think about 6 inches or so. And that way the porch is below the level of the general home's floors. That way water doesn't come onto the porch and then leak back behind walls or anything, because the porch is lower than the general floor area. And so I needed something to support the weight of all that concrete, and I wanted to minimize the thickness because I already had to reduce the wall height. The walls in my basement are, I think, 7.5 foot. It's not a full 8-foot height, and so you're already kind of constrained for space. And I wanted to use that space beneath the porch for another bathroom, a restroom in the basement. And so I was really hesitant to put a very tall beam down there. So rather, I used something that was inexpensive, whereas an I-beam would have been expensive. The rectangular tubing was not. It had a fairly thick wall, and essentially is the same as an I-beam because you've got a fairly large flange at the top and bottom. Now, I chose a square tube rather than a rectangular tube because I wanted to get as much flange out of it as I could, so I wanted the width to be as large as it could be. I suppose I could have bought a rectangular tube and turned it on its side. That, in hindsight, may have been a good idea, but it's held just fine, and I've jumped up and down on the porch, and it's extremely solid. So, and I did a lot of calculations on it as well to make sure that it would be very strong. So, a rectangular tube or even a square tube is not a terrible shape as far as being an efficient beam goes. Round tubing, though, is not the best because if you think about what's going on with round tubing or even round pipe, the material at the top and at the bottom, there's just not much of it, right? Because the pipe tails off fairly quickly. Now, it's not terrible because at the top it doesn't come away from the outer fiber or the outer dimension very quickly, so it's not an awful design. And if you think about go-karts when you were a kid, most go-karts are made out of round tubing or round pipe, And it's strong enough for the application, it's cheap enough, so it's an acceptable use of the material, but it's not necessarily the most efficient beam shape. So really the thing that makes a beam shape efficient is the material being far away from the neutral axis and concentrating more material farther away from the neutral axis. That's what really gives a beam significant strength.